So we have to do this.
What I did is,
Okay, done.
what happens is, guys, I would update the term, and so they would accept the default technologies. So what I did is
I think we got every time
so it's creation once and then
and
just
did
all the
talking stuff, some of the lines.
So it creates the arguments once it's
Yeah,
table,
okay.
and then even though it still sends those five
Smile on.
every meeting.
That's wrong. So here's the reason.
So they're not used to
all this thing. The page doesn't necessarily need to be
We'll
So what you need to do is everything should go through
So once you send once, it's going to
So
be all
you need to check if everything is written in such a way. If it's inside of the
how do you
all through the two on that
I
particular page. So you don't call it a file.
Does that make sense?
Yeah.
No, so here's the thing. So everything should operate on page. Nothing should go
Wasn't like
except where writing is and writing. Does that make sense? So page, so yeah, so every time when you actually want to touch like that actually get two places, you can do that. First of all, get a top buffer from get a buffer page from file, or you link to back into the base. So you write that page back into file.
Yeah.
Does it make sense?
I was scared because I have a lot of personal.
Anything other than that, you should do that on pages.
Like just
Does
things
that
that
make
make
sense? It's an automatic system that actually handles a set of pages.
Because I first just put in
Automatically will shift things and push things and get things. Does that make sense?
Yeah.
So you should not break that instruction.
Okay, I'll try, so that's what I do.
That first is
Then I should ask it. Oh, yeah.
It was weird too. This
Yep.
was probably like 2 weeks.
Yeah. So
Yeah.
I don't think I have to.
But they just didn't test it first.
the tests in like C are way more challenging.
Oh.
Like it was like 2 minutes.
Canada.
It was like sitting about like yeah.
The test is do you do the
I haven't tried. I did it on 2B2 or 2A.
Let me know if you can raise my because I get an error somewhere. But I don't think there might. I don't think there's a way to do that. Just based on how there's no
Well,
way
if
to
it
raise
was fancy now, I would say that.
Yeah, I did.
Yes.
But yeah, because that's like
Because I thought about it and I was like, all I did was add the persist calls.
the test
And
rate.
wherever I was already walking it. So it's like,
That's ridiculous.
So yeah, I did my turn.
Yeah,
So the date is already.
but then I was like, and then I would run like one of the terms. And last night I was like, what if I could figure out a way to run 2A, 2B, and 2C all at the same time?
Can I go test or something?
Sort it.
You don't have to do go test.
Let's just do that.
I saw it and I was like,
That's like some.
I was like, oh, I didn't know that. It was specific test. I just
Yeah, I found out
So
it's
what
like,
I can
so
do
it just,
is
it's a
read it something.
red table, so it's so like the 2A is the test that which is why he always has like 2A with the term shares.
That makes sense. I don't make your test just like that. It's a good way to do it.
Okay, so let's get started. I just did a quick count. We might just have about 7 lectures left, including this one. And that means, so I really need to, if you want to learn more about some additional stuff, in addition to the traditional database, then probably I need to keep it on schedule. Okay, so I would say probably the QO part, the query optimization part, could probably I can finish them by next lecture maybe. Then we will probably spend about 3 to 4 lectures on the transaction, concurrency control, and recovery part. Then after that, we might just have maybe 1 to 2 lectures left. So that's where we might spend some time on some additional topics like Spark, and also if you want, we can do a review session as we did in midterm. Okay. Yeah. So I don't think there's enough time at the end of this semester for us to review everything really in details. So if you do have a lot of questions about the homework assignments or the course materials, please come to office hour, maybe around the finals, okay, before the finals, so that you will do well in the final, okay. Right, and also regarding the projects, how's project 3 going so far? It's good. Yeah, I'm sorry. So if you haven't started, then that's probably too late. But like the due is tomorrow, and I'm sorry, I really can't give you any extension for this project because of the tight schedule. We still have 2 left. What I'm trying to do is maybe the next one will still be the normal project, and the last one, maybe I will just require you to do half of it. And that basically means, so basically the last project is on concurrency control. It doesn't involve a lot of coding. But the only issue is that one of the tests is really hard to pass. So maybe we skip that test. But if you do it correctly, we give you an additional bonus on top of that. Okay. So that's my plan. So yeah, if you have any other thoughts, please let me know. I'll consider it. Okay. So let's continue with tutorial optimization. Yeah. So basically, last time we talked about a very simple query where we are joining 2 relations, the reserve and sailor table, and we consider different plans like using page-oriented nested loop, the simplest possible join algorithm, and how do you like push down selection, push down projection, push down or materializing the intermediate results, how that could help in the I/O cost of your query. And we also talk about different implementation of this join operator, like you could instead use a sort merge join, or a block nested loop join, or if you have index, which we haven't talked about, if you do have index, we have more alternative plans. Okay, so let's see this example. Suppose we have a cluster index on BID of reserves. Okay, so it's on this column on BID of the reserves, and then we are joining red. No, not joining. So if you have a cluster index on PID, then we can use this this cluster index to perform the filter here. Okay. So basically, this selection operator select PID equal to 100 can be performed just with the cluster index. So with a cluster index, the cost of scanning a specific range is just the number of pages in the data entries you have for this particular range plus the search cost. Okay, so using the same example, so we have 100 votes, and 100 votes, and we have 10,000 pages in total. So that roughly gives us 10 pages for BID equal to 100. So the I/O cost for this part, for the selection part, it's just about 10 plus the tree height. Okay. So basically, I'll just write tree height. Okay. The tree height is normally small, usually small. It's just maybe for a small relation like this, it's just 10,000 pages. 1,000 pages, then the tree height is probably just 2. Okay, so let's just assume it's 2 here. Okay, then this basically the scanning of all the tuples from results that satisfy BID equal to 100 is probably just cost you 12 IOs. Okay, instead of 1,000 if you do the heap scan. Okay, that's the use of cluster index. And also, if you do an index nested loop, that's to say if you do have an index on sailors, then you could do an index nested loop. Okay, then you do not actually need to materialize this outer relation, right? To use index nested. It just loops through every tuple that satisfies the condition on the left, and then probe the index on sailors for the corresponding tuples in sailors. Then you scan through all the sailors. Okay. So if you do have that, that's to say we have say an unclustered index on SID. Then what's the cost of this query? Okay. So on the left, you basically have roughly 12 IOs, and on the right, for each of the tuple that matches the condition, you need to search for the corresponding sailor tuple with SID equal to the tuple you have on the left. Then how many tuples we have for reserve? Okay, it's gonna be about number of tuples on the left is going to be 100 times 1,000 times 1/1. Okay, that gives us about 1,000 tuples. Okay, and then it's kind of hard to estimate what is really the IO cost on the right, because for each of the search, you might need to pay a little bit IO to find the corresponding tuple. And also, when you reach the corresponding SID, the issue is that you could possibly land on different key pages. If it's unclustered, then some of them will be on the same page, some of them will not, right? On two adjacent accesses, depending on your buffering, how large your buffer is and your page eviction policy, you could end up with either one additional IO to fetch the actual tuple or not, right? If it's already in the buffer pool. Okay, so then typically they use estimate for that. In this case, it's just using a factor of 1.2. Okay, this is a magical number. So sometimes it can be estimated by the height combining how large your buffer pool is, so that how likely some of the adjacent or access to the actual tuple that is nearby, how likely they are actually accessing some page that's already in the buffer pool. Okay, so this is just a number that's estimated by the core engine. Then if you stick with this number, then basically you pay 10 IO, actually it's 12 IOs. Then you pay a cost of 1,000 times 1.2. Then by adding them together, it gives you roughly 1,212 IOs. Okay, roughly like something like that. Right. So it is really a little bit hard to estimate the real cost of index nested loop because of the buffering issue, and also like the tree height. It also depends on the tree height. Okay. So any questions about this index nested loop? Okay. So then that's basically everything. And also we didn't talk about hash joins, right? So if you are doing a hash join, then it basically follows 3 times both relation, right? Unless everything fits in memory. Then let's view this from a bigger picture. Like let's view the whole process in whole. Okay. So basically, you have a closed set of operators to choose from. Okay. And optimize on. Basically, your query is going to be translated into a relational algebra, which consists of a limited number of operators. And for each of these logical operators, you have different choices of implementations. Okay? And also, you might also rearrange these relational operators so that it's equivalent to the original plan, right? So then that involves like selection push down, projection push down, or join reordering, something like that. And also to correctly estimate the cost of your query plan, you probably need to know, first you need to have a model for each of the implementations, right? You need to have a model of costs for each implementation, whether it's based on expected number of IOs or expected CPU time or a combination of them, or some more complex. And also, to correctly estimate that, sometimes you need to correctly estimate what's the size of, what's the output size of each operator. Like when you do a projection, not projection, when you do a selection, what's the percentage of tuples you have relative to the total number of tuples, right? That actually helps a lot when you decide what's the IO cost and CPU cost for like computing that, and also that has an impact on the downstream operators. And also, like for projection, it's actually easier. You just look at the schema, then that's fine. But in reality, you have variable length fields. So for variable length fields, it's really still an estimate, because sometimes some fields could be longer, some fields could be shorter. And then it's still a rough estimate based on your statistics stored in your catalog, right? And so since we have so many things to consider, we really need to have a very efficient algorithm, search algorithm, to help us to find a good plan, right? So as we talked in last lecture, in an ideal world, we want to have the best possible plan, but that's usually too expensive to have, or simply to say it's impossible to have. Okay, so in reality, our search is geared towards finding a good plan, just not the worst one. Okay, just don't do anything too much. Just try to give you a fast enough plan. Okay, so that's the query optimization. Alright, so in this lecture, we will start with something simple for the query optimizer. It's called System R style optimizer. The System R is the very first relational database developed by IBM. And then they proposed a very classic optimizer for like optimized general queries. Okay, so basically we will just use this particular style of optimizer. This is a very simple one, and if you look at any database, today's database, it must be more complex than this. But it's still a building block for a lot of them. Okay. Then, so basically this kind of optimizer works well for less than 10 relational join. Okay. If your table is exceeding, your query is exceeding large, that you have too many tables to join, then this probably won't work. Okay. As we will note later, that is because one of its components is going to run in 2 to the power of number of tables in your query. So that's why it's going to be really, really slow if you try to use it on a really, really large. Okay. And also the cost estimation in this kind of optimizer is really, really exact. Basically, what it tries to do is use something like number of IOs times a factor plus estimated CPU time. Okay. So it's not going to be exact because it basically assumes every IO is has uniform access, uniform time, right? That's not possible because you have random IO, sequential IO, different kind of secondary storages like SSD and HDD. It's not realistic to have a single factor for IO. And also the CPU time is also not uniform as you might think, right? It could be some issues like if you have a Newman node, then you have different kind of access cost for different regions of your memory, and also there are caching issues, right? So this is really, really inexact, but it's okay in practice because kind of if you have a really bad plan, the worst kind of plan, it's going to be this number, the estimated cost is going to be orders of magnitude larger than a good plan. So that way you can avoid the bad plan but choose a reasonably good plan. Okay. That's why it works. And also for the plan space, it kind of simplifies things by only considering the space of left-deep plan. This I will talk about this later. This is just to say, basically, it only considers a constrained class of plans. Okay, it doesn't search all possible plans. Okay, so that's why it might never end up with an optimal solution. Okay? Even if you allows it to search for a limited number of time. Okay, but then it still doesn't end up with the optimal solution. And also, it tries to avoid partition products. That's just an intuition, right? You try not to do any partition product because that's going to be expensive. But actually, in reality, there could be some plans that with partition product that's cheaper. But that's just this is an intuition that works for a general, common core, but not for expertise. Alright, so yeah.
So in what situations will
Okay, so basically, so if you do chain join, like you join A and B and C, right? What you want to avoid is you first do a partition product between A and C, okay? Because that way, you cannot eliminate anything, right? Until you start plugging the B, right? But there are certain cases like if your A table is really, really small and C table is also really, really small, but B is a huge table. In that case, it might be cheaper actually to first do a partition product between A and C, then join B because the selection is really selective. Okay. But that's just I would say that's just a special case. And probably this kind of system R style optimizer won't consider that as a valid plan because usually it doesn't happen. So then the system R style optimizer partitions or parse a query into a collection of query blocks. Basically, it treats a basic block like first do this nested block, then plugging that number into another block. That's one possibility. Or you could transform some kind of nested query into a join query. Then you have a single block to optimize. And it kind of enables more optimization towards that. Okay. But for simplicity, let's assume we just independently optimize these blocks in this kind of optimizer. Right? So then, for each of the block, we first consider all the access methods for each relation in the form call. Okay? So basically, you choose a cheap, the cheapest possible access method for each of the relation here. For example, for sailors, if you have both an index and a heap, you could choose to either read everything from the heap, or you could also probe, if you have a selection predicate, then you probably can probe for a particular range and scan the index. Okay, so that's different access methods. So basically, you basically choose the cheapest one to like get tuples from that particular relation. However, sometimes you might also need to keep some of the interesting plans where, say, it has a particular order, so that it can enable other kinds of implementation of other downstream operators. Okay, so that's something to consider. But we will talk about this later. And then, so that's the first step. This is just an overview. But then the next step is to consider all the deep, left deep join trees, where basically, so if you do a join, you can have different orders of join. Then here, a left deep join tree is basically, as its name suggests, the right branch of a node is always base table, and you only join intermediate results like this. Like every time you first join two base tables, then you join that intermediate result with a third base table, and so on. You never have a bullshit plan like you first create two intermediate join results, then join them together. You never do that. That's the space of left deep join. And as you can see, that's actually not optimal, okay? Because you don't actually consider all the possible join order. But this is sufficient for a common point. Okay. So we will still use the same example here. Let's say, let's go through the workflow of this kind of optimizer. So in the first step, you translate a SQL into relational algebra. Okay. So let's suppose we have this query where for each of the sailor with the highest rating over all the sailors, and we require each sailor in the result has at least 2 reservations for red points. Then you find for each of such sailor, you find its ID and the earliest date on which the sailor has a reservation for red points. Okay, that's a complex query. Anyway, so then you have this kind of query. It has a nested query over here where it's select max from something, right? So basically you will have 2 blocks over here. Okay. Then you translate that into a relational algebra. Notice that we do have some additional operators that's not in the relational algebra, like having and group by. Okay. These two actually you cannot express them directly in relational algebra because they actually kind of produce. They basically they work on a multi-setting subset. That's why they don't really exist in relational algebra. But for a real database system, because you do have this having group by, so you have to add those operator into your relational algebra or an extended version of relational algebra. Okay, so then you have you basically have these 2 blocks here. The first block is the same on the left. This is outer block. Okay, this is your outer block. And notice that we have this value shown in red over here. This value refers to the inner block over here. This is the inner block. Okay. So basically, the optimizer will try to optimize the 2 of them individually. Okay. Then, once you have a relational algebra, you try to derive some equivalent relational algebra plans. Like you could have different ways of expressing the same query. Okay, so here are some basic rules to derive equivalence. Okay, so for selection, if you do a selection where you select C1 and C2 and so on, then it's equivalent to apply this selection one by one. Okay, it's equivalent to separate that into different selection. And also, selection is commutable. That's to say, if you do a select C1, then on top of select C2 over R, it's equivalent to you select C2 over the selection of C1 on R. Okay, that's the commuting rule. Then for projection, if you do a bunch of projections, the cascade rule says it's equivalent to just do the outermost projection. Okay? That is because whenever you do a projection, it must only refers to the attributes that's present. Okay? So when you do this AN, it's guaranteed that AN minus 1 is a strict subset, just a subset of AN, right? AN minus 1. So this AN minus 1 must be a subset of AN. Okay? Otherwise, this projection won't apply. Okay? So that's why you basically, when you do a sequence of projections, it's equivalent to just do the outermost projection. That's a cascading rule. Then for joins are this is quite similar to the addition in arithmetic, right? So basically, you have associative rule and commuting rule. Okay. So basically, R, if you first join S and T, then join R with them, it's equivalent to first do R join S, then join T. Okay. Provided that you still can apply the so basically, if R and S are joining on common attributes of R and S, and S and T are joining on common attributes of S and T, right? That's the associative rule. Then you also can commute join. Basically, R join S is the same as S join R. Okay. So that basically means we can do joins in any order. Okay. So really, this in any order actually includes those Cartesian product lengths. Like let's say we have an example like this. If you do R join S on some attribute A where R and S both have A, okay, and then you join T. S and T both have B. Okay, so what we really mean is that you could first do S join T, then join R, or you could just first join R and S and join T. But actually, this is also a valid. This is also a valid plan, but this is also possible during all of them. But how can you do that, right? This kind of the first join, if you use this or R join T join S, you first join R and T then join S. This plan essentially degrades to a Cartesian product in the first one, okay? Because here you don't have a common attribute, then the condition is basically just true. You provide anything in the Cartesian product, then join both A and B with S. Okay. So that's the plan we won't actually consider. Typically, we won't consider in a R style optimization. Then we have more equivalence rules, like so a projection commutes with a selection that only uses attributes retained by the projection. Okay, that's to say basically if you have a projection of A, and then you do a selection on some table R, then this is equivalent to select. First do select based on some condition C, and then do projection A on R. They are only equivalent if and only if every attribute used in C is also in A. Okay. So because if you do not have, if you refer to some kind of attribute that's not existent in A, once you do the projection, you cannot no longer operate on the projected results, right? And if you do want to push down the projection, if A is not a superset of the attributes referred in C, then you need to add those additional attributes to the projection list once you do the projection. Okay? One example is like this. So if you do projection, SID, select reading greater than 5 on sailor, right? It's not equivalent to first do projecting SID on sailor, then select reading greater than 5. That doesn't make sense. But what you can do is add the additional reading to the projection list so that it can be commuted. Okay? So basically it works like this. You do reading greater than 5, and you do a projection SID and reading on the sailors. Then this projection is going to be able to be pushed down. Okay? That's the first move. And also, like the selection between the attributes of two arguments of a cross product convert to basically that's a join. Okay? Maybe a general join or equal join, depending on your condition. That's just basically a selection of some condition R cross S. That's a join. Okay? That's basically a join based on C. Okay? That's a loop. But that's just actually the definition of join. And a selection on just attributes of R commutes with R join S. That's something we call selection pushdown. Okay? Basically, if you have a selection that only involves attributes in R, then you can push the projection. If this projection only involves attributes in R, then you basically can push this projection directly to R. Okay? This is something like when we discussed that the simple plan for joint tables. If you have like select rating greater than 5 on sailors, that's only involving the the attribute in sailors. So you can basically push that directly on top of the heap scan, so that you have a smaller intermediate result to be drawn. Okay. Then you probably end up with a lower amount. That's a really useful one. Selection pushdown is a really useful one. And then if a projection follows join, we can push it by retaining only attributes of R and S that are needed for join, and also the ones that are retained by the projection itself. It's basically the same as the first group. Okay? So whenever you need some additional attributes when you push down the projection, you basically add them to the projection list. Okay, so far so good. Okay, that's about the equivalence of relational algebra. So when you are trying to optimize things, you can consider all kinds of transformations mentioned before. Okay. Then for each of the plan, for you to actually to be able to reason about which one is better, you have to have some kind of cost estimation, right? So here we've already talked about this. In system R, the cost basically boils down to a single number like this: the number of IOs times the factor. The number of IO plus a factor times the number of CPU instructions. Okay. So this is by no means is not accurate reflection of the actual running time. Even if you think that's just a constant factor times of the running time, that's not the case. Okay, because it oversimplifies the computation model you have. You have a lot of hierarchy and different characteristics associated with IOs in your system. But it's a good enough estimation, and it's simple enough for them to implement. Actually, if you think about that, System R was developed around like 70s and 80s, if I remember correctly. That's the age where you barely have the C program language just come, right? So that's the very early stage of computer science, right? So it really needs just a simple enough thing to implement, and as long as it's good enough, it works for them. And then so to estimate this cost, you must have to estimate the number of IOs and CPU instructions for each of the operators in the tree. And for you to do that, you actually need to know the size of all the base tables and including the results. Okay? So that's something we will talk about just next. So to do that, we actually maintain a lot of statistics in the catalogs. So basically, your catalog will typically the catalog will at least contain this kind of information. First, you will have how many tuples you have in a table, how many pages you have in a table. That's the bare minimum statistics. And also, typically, you will have the number of distinct key values for each index. Okay. The intuition is that whenever you build an index, it's normally that's to say basically the DBA wants to optimize for join or selection on that particular attribute. So when you actually do the projection, the selection or join, it's really important for you to know the number of distinct keys to be able to actually calculate how many tuples are in the result, right? And also they will keep the low and high keys, like the smallest key and largest key. Okay, so let's say here's a really intuitive example. What's the second number for the result? Okay, suppose we have an index in BID. Then we will keep how many distinct BIDs we have. This is the 100 here, right? Then we will probably just keep the values, the smallest value and the largest value for BID. Right? So let's say our BID is in a range of 1 to 100. Okay. Let's say our BID is from 1 to 100. Then if I do BID equal to 100, use that as a selection. What fraction of the tuples you are selecting based on this selection? It's going to be just 1 over 100, right? Because like 100 is in the range, and there are 100 distinct keys over here, and it's here you only have 100 distinct keys in the range. So that's if you are assuming uniformity, then it's basically 1 number. Yeah.
Are these statistics exact or like probabilistic?
Right. They are basically so they are not probabilistic, but they are not exact either. They usually are just approximate snapshot of that. So basically, whenever you do some updates, it might not get updated very often. Just after a bunch of updates, it gets updated once. So it could be inexact, and it could not. Maybe it doesn't have any value. But like if you do update this frequently or from time to time, then it will be accurate.
Can you use something like streaming algorithm, like type log or root filter or series?
Yeah, that's actually a very good idea, except that the only reason why they don't actually maintain the exact count is not for the cost or costing reason or the space reason. It's basically because the locking. Okay? So whenever you do an update, you lock the actual record you are updating and a bunch of indexes, right? If you were to also update these catalogs, it's going to take additional logs. But yes, so if you are trying to find this number of distinct values, it's definitely useful to use approximate. Maybe one thing that you should consider is that if you can leverage some kind of a log-free data structure, like if it's just count, you could use atomic integer, right? You could use that, then probably you can avoid logging problem. But again, log-free is not free, so that's still an issue. And then, yes, we talked about the number of distinct keys and the range of keys. And also, we might have the tree height and number of index pages we have for each index. This is actually really important, especially the index line, like the tree height, because it's directly associated. If you use something like index length loop, you pay that search cost every time you probe the linear relation, right? So that's a significant portion of your I/O cost. So this is a really important statistic to have. and number of index pages are red. So maybe this is important, but I don't really see it. Yeah. Well, it's definitely useful to have a statistics for the number of data pages, the lead pages. Yeah, and the point is the catalogs are updated periodically. Actually, maybe I would just say maybe. So in PostgreSQL, you have I think you have a method called vacuum, something similar to vacuum. Vacuum is for garbage garbage collection. And there's another. Oh, it's called analyze. Yeah. So basically, I think what Postgres does is sometimes it doesn't keep your statistics up to date. So then you do a manual update of the statistics by calling the analyze. It basically scans all the tables. That's going to be expensive, but the obvious thing is that typically if you have a database like customer facing, for placing orders, it will have peak time and non-peak time, right? You could just do the vacuum and analyze in say 3 p.m. 3 a.m. Right? When nobody is placing orders. So more details. We will talk about more details about how to actually maintain some more advanced statistics just for estimating I/O cost. The sizes. And then we define. So consider a query block. We define something called a reduction factor or a selectivity. Okay. The word selectivity is actually easier to understand because basically, if you have a bunch of conditions, they will select only part of your tuples, your base tables. Okay. So what fraction do you select is a really important thing to know for you to actually optimize your query, right? Because like when we consider alternative plans for the simple query you mentioned earlier, we actually need to know what's the end result of the selection, what's the end result of projection. How many pages you have there. So it's really important to know how many tuples are going to remain after you apply these filters. Okay? So we define the reduction factor as the number of tuples in your result divided by the total number of tuples. Okay? So for a specific, so let's say some of the term is based on one of your relation. Then that's basically after you apply this. Let's give you an example. Okay, so let's say you do something like select rating greater than 5 and on sailor. Okay, so the reduction factor or the selectivity of this particular selection is going to be the number of results of that divided by the number of tuples in sailor. So that's the RF of this select. Okay. This is going to be the reduction factor of this select. And also you could also define this on multiple tables. Like you could do reduction factor of join, right? Like joining a sailor and reserve. Okay. So let's say you are joining reserve and sailor. Okay. Then the reduction factor is basically the number of join results divided by the Cartesian product, okay, divided by the size of Cartesian product. That's going to be the reduction factor of a join. Okay. So basically, in general, if you have a bunch of relations. A bunch of filter conditions. The reduction factor is the cross product of all the tables involved in this query, and the size of that divides the total number of results as a result of the query. That's the definition. So we have some. So actually, this is really hard to answer this question. So what's the reduction factor or what is the selectivity of a particular selection predicate? Unless it's something unless you could make some assumptions, or you have some more advanced statistics, or you have some additional information from that. Okay. So here we consider a very general case. Let's make an implicit assumption that the values are always uniformly distributed, and also the terms, the terms or the conditions, the conditions are actually independent. Okay, that's definitely not the case in reality, but it's just an assumption. Okay. So for this kind of term, if you for the first kind of term, you have a column equal to some value. So basically, you select some tuples based on a particular value in a particular column. Okay. So what if you assume the uniformity of the values, then the reduction factor is exactly 1 over the number of keys on that column. Okay. Right. So let's give an example. So suppose you do BID equal to 100, right? So in total, you have 100 times 1,000 tuples. If you do assume the both IDs are basically uniformly distributed, so no matter what the 100 distinct both IDs are, there will exactly 1 over 100 of the tuples having the same both ID, 100, right? So that's why the reduction factor is going to be 1 over 100. Okay? And then if you have a term, this is for join, right? This is for join. If you have a term like column 1 equal to column 2, usually these are two columns in 2 tables. Okay, 1 column in each of the table, and it's doing an equation. Okay. Then the reduction factor is basically 1 over max of number of keys of the first column and number of keys of the second column. Okay. Why is that? This is because, so let's say you have n tuples on the left, and you have n1 tuples on the left and n1 keys on the left. And also you have n2 tuples on the right and n2 keys on the right. Okay. Let's just assume n1 is greater than n2. Okay. Or greater than or equal to n2. So then let's say how many corresponding tuples you have on the right for each of the let's see really the other way. So let's see for each of the tuple on the right, okay, how many corresponding tuples you have on the left on average? It's gonna be just n1 divided by n2, right? Because on the left you have n1 over n2 tuples, and on average there will be just n1 over divided by n2. Right? No, sorry, divided by n1, right? Because you have n1 keys, so for each of them, the number of tuples having the same key will be n1 over n1. If you do have some matching tuples on the left, then the number will be n1 divided by n1, right? That's the degree. Then if you follow that, then how many tuples you have in the join result? It's going to be n2 times n1 divided by n1, right? Because for each of the tuple on the right, you have exactly about n1 divided by m1 tuples on the left, matching matching key. Then the total number of join results will be just n2 times that number, right? Okay, so the question is, can we do that the opposite way? Like we start from the left and to see how many tuples we have on the right. That's also okay, but if you do a calculation, it's going to be, so for each of the tuple, n1 tuple on the left, they will have exactly n2 divided by n2 tuples on the right, have the matching key. But look, these two numbers are not the same, right? Why is that? Because for some of the keys on the left, there's actually no matching keys on the right. Because we say n1, let's suppose n1 is greater than or equal to m2, then there must be, if it does, m1 is actually greater than m2, then some of the keys on the left must have no matching keys on the right. Right? So that's why this is actually not fair. Right? So if you do assume uniformity and you assume every key on the right does have a matching key on the left, then you estimate the reduction factor as this. Okay? 1 divided by max of number of keys on the left and number of keys on the right. Okay? And this is because if you divide the number of joint results by n1 times n2, which is the size of the Cartesian product, you exactly get this reduction factor. Okay? So that's for estimating the selectivity of the joint condition. Okay? And then you could have the term that has some column greater than some constant value. Okay? So this basically, if you just assume your values are evenly spread in your range, in your total range, like from low to high, from the smallest value of this column and the largest value of this column, then basically that's the way to do that, right? So basically it's something like if you draw a range, that's the low is the smallest number for column, and high is the largest one. High is the largest number for the column. Then if you are saying the column is greater than this particular value here, then this part takes exactly this portion of this whole range. If you do assume uniformity, then that's the reduction factor. Okay. Okay, so as we said, you only have those statistics if you do have an index on that particular column. But what if we don't? What if we don't have an index on that column? Then basically you do something really, really dumb. You just assume it's 1 over 10. Why it is 1 over 10? That's no really a good reason for that. Okay. Okay, so can we do that better? Like, can we really get a better estimation of the sizes? As you see, the estimation are really based on very lousy assumptions, right? So for a better estimation, we could use a histogram. Okay. So we have a lot of kind of ways to construct a histogram for a particular column. Let's say your column have a bunch of values like 2, 2, 3, 3, 4, 4, 5, 5. Okay, you could probably construct a histogram like this. Construct a bucket for 2, 2, 3, and there are 4 elements there. And you could also construct a second bucket where it's 4, 2, 5, and there are 4 values. Okay, so that's just an intuition of the histogram. So basically, these are the items, and you form that into coarse grain buckets. For each bucket, you can count how many tuples you have in there. Okay. And then, suppose we do have 2 kind of histograms over here. Okay, we could have an equal width or equal depth. For equal width histogram, basically you require each of the bucket has the same width. Okay, so basically the first one, suppose the width is just 1. So then for the first bucket, you count how many tuples are having the column value of from 0 to 0.99. Okay. For the second bucket, you count how many tuples are there with the value of 1 to 1.9. And so basically each of the bucket have the same width in the value. Okay. And you count how many actual tuples fall into that bucket. But there's another option where you are equal depth histogram. Basically, you try to minimize the difference between the number of values. Okay? So you could have, for the fourth bucket, you're using 3 to 3.99, and you only end up with one value. Okay, so that's actually then for the next one you have 4 to 4.99, you have 8 values. What's the issue with that? So as your variance of these buckets, the number of values of this, the variance of number of values of these buckets gets higher, your estimate is going to be less accurate. Okay, because how we actually use these buckets? So suppose we want to find how many values are from 4 to 4.5. Okay, let's say we want to find how many tuples you have from 4 to 4.5. The only thing you could do with the equi-width is to use this bucket, 4 to 4.99, and you notice that 4 to 4.5 is actually half of that bucket. Okay, but you only have one cut. How do you estimate that? That's basically you assume uniformity in that bucket. So that gives you about 4 tuples. That's 8 divided by 2 equal to 4 tuples in 4 to 4.5, right? But that's rough. What if your almost all your tuples from 4 to 4.99 are near 4, or they're near 4.99, then your estimate is really off. So what you can do is you require the number of values of each of the bucket to be almost equal. Okay. Then you have these kind of things. So from 3, you do not end with 3.99 for this bucket. Instead, you use 4.05. Then you end up with 3 tuples over here. Then from 4.06, you go until 4.67, and you have 3 tuples over there, right? So basically, you divided this 4 to 4.99 into 2 entire buckets and some part of the bucket over here, right? So if you compute that this way, you get a different answer. Okay? So basically here, if you are calling for 4 to 4.5, you notice that 4 is within the fourth bucket, and 4.5 is in the fifth bucket, and they are both part of the bucket. Okay? So basically, you use the same formula here: 3 times 4.05 minus 3 divide 4.05 minus 4. Okay, so basically you still look at the portion of this of your range. That's the estimate for the number of tuples in the fourth bucket, so that it falls into 4 to 4.5. And then you compute how many tuples are there that satisfy this range in the fifth bucket. Then it's going to be 3 times 4.5 minus, it's 4.67 minus 4.06, and 4.5 minus 4.06, right? So this is basically the range is looking like this. So this is your bucket of 3 to 4.5, and this is bucket from 4.05 to 4.67, right? And then you know your range is actually this range. Okay? It's going to be 4.0 to 4.5. Okay, so you compute the portion of this, that's this, right? And you compute the portion of this, that's what you do. Okay, then you take a uniform, you assume uniformity, you get the number, right? And this is a better, it's actually a better estimate for the number of tuples in the range. So let's do a visual comparison between equi-width and equi-depth. So basically for equi-width, the width of each of the bucket here, so basically for each of the, on the x-axis, it's the value. And for each of the buckets, you have a bar. Okay? The bar height is the number of tuples you have in that bucket. Then for equi-width, basically each of the bar have the same width. Okay, that's very intuitive. But for equi-depth, each of the buckets will have different widths, but they will have roughly the same height. Okay, that's the requirement. So So of course, so if you have unlimited space, then basically the best histogram you can get is exactly each bucket has exactly one, or everything in one bucket has the same map. That's the best thing you can hope for. But that's essentially between index, right? That's too expensive to have. So in reality, you might need to construct the equi-depth histogram with a fixed cost, okay, storage cost. So let's see this, right? So in reality, to construct the equi-depth histogram, you need to first define some kind of objective. The objective is actually to minimize the variance of the height. No, not actually height. Actually, it's to minimize the variance in each of the buckets. Okay. Oh, I'm sorry. Right. I was wrong actually. So I will talk about this later. This is more complex. This is optimal. That's to kind of reduce the variance within the bucket, because we do assume uniformity within the bucket, so we might want to reduce the variance of that. But let's go back to equi-depth. Okay, let's go back to equi-depth. Equi-depth is a little bit harder to construct because you want to minimize the variance of estimation errors from all buckets. So then you might want them to have roughly the same height. Okay. Then what you can do is basically so if you know what's your cost. Okay. So let's say our budget is we want to construct 6 buckets in total. Then you need to first define what's the best thing you could do for the equi-depth histogram. Okay, so basically what you could do is you can define you want to make sure the variance between the buckets are smallest. Okay, so you might want to just reduce the variance of the bucket height. Right? So how do you actually do that? I think one thing you could do is using a dynamic programming algorithm, right? You could try to minimize this variance value. Okay? Or you could do it using a greedy algorithm, but that doesn't guarantee you the optimal solution. So I will basically just omit the details. So you will, in SimpleDB, you're going to build, so in the next project in SimpleDB, you're going to build an equi-width histogram for integer and string. Okay? So you could just build the equi-width, not the equi-depth, because that's a little bit harder to do. And also there's another thing to note is that when we have some partial bucket, okay, once our range only covers part of the bucket, we can only get an estimate by assuming uniformity among the bucket. Okay, so then if your variance amount in the bucket is really large, like this one, okay, if you have a bucket looks like this one, okay, then the bad thing is that you could end up with a very inaccurate estimation if your range happens to cover this range, right, or this range. Okay, if you just cover part of them, you could end up with a very bad estimation because one of them is so large, one of the value has so many duplicates, and the other value has so few duplicates. And if you take an average of them, it's not close to either of the true value. Okay. So then, what you might want to do is to minimize the variance inside each of the buckets. Okay, but that's kind of like if you just look at the variance of each of the bucket, it's actually a multi-objective optimization problem, right? Because you want to minimize all of the variance. That's actually not easy to do. So instead, we define something like this. It's called a V optimal histogram. So this is a cost. Inside this term is something similar to the variance, except that it doesn't divide the square difference between the average and the actual value by the number of distinct values in the bucket. Okay? It just sums everything up. And then this has a benefit that you combine all the variance into one single object. So actually, so if you can achieve this V optimal, I think that you can somehow guarantee the accuracy of your estimation. But the V optimal is not easy to compute. This requires a dynamic program algorithm runs in, if I remember it, it's O in square or cube. Yeah, maybe it's O in cube. So this is not easy to compute. But those are the different options, like better than the equal width histograms. Yeah. So for here, really, it's just right. So for here, really, the really important issue is for you to understand what's the use of how to use a histogram and how to construct an equal width histogram. Okay, that's the important take-home message. Okay. So we've already talked about how to answer the queries using a histogram, but we haven't given analysis about the errors. So basically, if you have a histogram that has like the maximum error, the CB is actually the maximum error between an estimation and like the total number of elements of your actually. So CB is the maximum number of elements in one of your buckets. Okay, so that's the maximum count. So if you have a partial range that only matches part of a bucket, what's the maximum error you can get? That's basically the number of elements in that bucket. Okay. So if you have an estimate like this, the maximum error between the actual value and the value you get is at most CB. Right? Okay. So one example is that, so if you have a bucket like this, then all of your value are concentrated on the second half of that. Then when you do an estimate over here, say let's estimate how many tuples we have in this range. So what result you get? So suppose this bucket has CB result, and this is the middle point of that. Then you get roughly CB over 2, right? And then the error is going to be just CB over 2 minus CB. Okay, it's going to be CB over minus 2. Right? And also, this is just an example. So maybe your bucket is so skewed that only the largest value in your bucket has some count. Okay, all of your mass concentrates on the high range of your the largest value of your bucket, and you do an estimate of roughly the whole range except the largest value. Okay? Then you can convince yourself this is going to be near minus C right there. So the maximum error you could get for one of the buckets that has partial matching is at most CB. But for a typical query, you could end up with at most 2 such partial matching, right? One at the beginning, one at the very end. Then the maximum error is just 2 times that. So then, for join, let's think about the estimation for join. So does the above really make sense for joins? Does the size estimation we used before really make sense for joins? So actually, in common case, it's okay, right? So if you are joining a primary key and a foreign key, the reduction factor is okay, right? Because the maximum number of keys of your primary key is going to be like this. So if you have two tables, reserve, join, saver on SID. SID is a primary key on the right and foreign key on the left, right? So then, how many distinct keys you have on the right? It's exactly the number of tuples on the right, because it's a primary key. And then on the left, there's no guarantee, right? But anyway, what's the size of that? If you do have a primary key and a foreign key, once you join them, because the foreign key actually requires referential integrity, which means every foreign key in your table that appears in your table must have a corresponding primary key in the table that it refers to, right? So for any SID over here, there must be a corresponding SID on the right. Okay. So basically, the size of this joy is exactly the size of R, right? So then, if you compute the reduction factor, it is actually okay, right? If you compute the reduction factor will compute it as 1 over max of number of SID in R and number of SID in S. Right. So then this is probably just fine. Because like if you do the computation, it's so if you're typically if everything on the left on the reserve table is referencing some value in the S, and we do have a matching, right? So then that typically that means the size of R is greater than your S. Then you get no, not really, not really. Yeah, sorry, I'm wrong. Yeah, so the only thing, so that's actually right. You could end up with some right. So I was thinking about this case. So if you have a table like this, so if your sailor is looking like this, and for the normalization purpose, you split that table into a smaller one. Okay, that's R. Okay, and you are joining that back to S. Then probably the end result is exactly the size of S. Right? In that sense, the estimation is good. But in a more general case like this here, for reserve, it's not likely that every SID will have some entry here, or it's not necessary that each SID has exactly one appearance in reserve. Then that doesn't make sense. Okay? So then your estimation of the reduction factor really needs to change. Okay, for primary key and foreign key. Okay, so what's the result? So as you know, the size of join is exactly the size of R, right? So let's compute the reduction factor. It's exactly the size of R times divided by R cross product S, right? So that's the size of R divided by the size of R times S, and it gives you exactly 1 over S. Okay, so that's the way you treat the special case of joining primary key and foreign key. And this is really the primary key and foreign key join are extremely common case in database joins. Okay, I would say almost all efficient queries you might see all involves all the primary key foreign key joins. You seldom join like unrelated columns or like non-key columns. Right. So that's the general case. Right. And also, So here we're saying, so if you do a joint where A is not key, right? If you do a general joint where the A is not a key, then you could end up with two estimates. You always take the lower estimates for that. Okay. Why is that? Why is that? This is exactly the same reason we talk about the estimating. Okay. So this is exactly the same thing we've talked here. What's that? Right. When we are computing these reduction factors, we have two ways to do it. One way is from left to right, the other is from right to left. Right? You always take the lower because it's more likely for the relation with more keys than the other one. It's more likely that one will have unmatching tuples, right, in the joint result. So then you basically, if you estimate the reduction factor as the smaller one, it's safer to estimate that because it could be just closer to the final result. The actual joint size reduction factor can only be smaller than that. Right? It's actually, if you assume uniformity, then that's the upper bound. Of course, there are cases where neither of them hold, right? Like if all your tuples in both tables have the same key. Okay? Basically, that's a conditional product. You can never correctly estimate that with a dedicated histogram for that. Right. And also, yeah, we didn't roll it down over here. If you do have a histogram, the thing you could do for estimating joint size is basically look at the matching ranges of these two histograms. Okay. If you have one histogram for SID for Sailor and one histogram for SID for reserve, when you do the join, you could just pick for each of the buckets in one of your histogram and find the corresponding how many corresponding tuples you have using the other histogram. Okay. Then add those together, give you a rough estimate of how many join results you have. That's also a possibility. Right. So I think that's enough for this lecture. I don't think we have enough time for covering everything after that. Okay. So we will talk about how to actually optimize the joint order in the next lecture using a dynamic program. See you next time.
Yeah. And I know. Yeah. So I have a few good blocks. So I can pretty fast. All matches are going I don't really know how that happened. I used to send just the one previous.
Yes.
So I switched that to my luck is affecting now a lot.
Oh, beautiful.
But especially on if it's a big test,
So yeah, maybe it's past it still doesn't work. Yes, I do remember there are some strange things happening. But I mean, I could be
yeah. Well, do you spin off the routine for each seasons?
So it's hard to
And then how do you for each quarter, for each how many threads do you
So I have the job thread, and then I have the receiving client stuff thread.
Some of the imports and the
So
some.
that I'll get a call and I'll throw it off into the thread. And then I don't think I commit. I don't think I put a thread on the commit.
So you got two.
Yeah, somewhere around there. I mean, it's a lot in the terms of, especially when they're growing like crazy. There's a lot of threads, but
Yeah. No, there's probably stop.
yeah, I do stop threads like so it's usually on the job call, but I just surround it in a statement that says like, hey, have you been killed? Like I have a killed variable.
Yeah, I'm sure that's actually.
So because I actually ran into a bug testing on 2B, or no, 2A, I think it was. No, I can't remember, one of the two. And what was happening is that the old would still be alive in the next test. And it would like get RPCs and throw errors and cause problems. Yeah. So, yeah. Yeah. First day you want I like the way you guys conflict.
Here we go. I never really. Does this stay here? Or do we take this?
That's ours.
I never
Stop
use.
screaming on that before you shut it.
Yeah, that's a good call. Hopefully my